All right, so we just got done talking about radioactive dating. Now we're going to look at relative dating and how we uh, figure out which layers of rock are essentially the same age without putting an actual number on it. All right, um, we're comparing things. All right, this is older than this, that's younger than that, whatever. All right, so just looking at this picture right here, I have a little what's called an outcrop. It's basically it's supposed to represent four different layers of rock, four layers of sedimentary rock, pretty much. Um, if we look at this, knowing the order of operations of things, hopefully you know by now that the oldest layer is going to be on the bottom, number one, and the youngest layer is going to be on top, number four. We can take outcrops of rock layers from very widely spaced regions, and we can figure out a lot about them. There's a lot of principles that we use to figure these things out, and a lot of these things you kind of do without even thinking about what it's called. But we have names for all these things that we talk about, and that one we just did there, where you know the bottom layer is the oldest, is what we call the principle of superposition. All right? Now the key thing about this is that it has to be undisturbed layers. They can't have been overturned or faulted in any way or twisted, anything like that. So if we're just talking about horizontal layers of sedimentary rock, the bottom layer is going to be the oldest. That's the principle of superposition. All right? In other words, the deeper we dig, the farther back in time we see. All right, second principle we use when we're doing this is called the principle of uniformitarianism. It kind of means the present is the key to the past. So if we want to know what's going on in nature today, we have to make the assumption that those same processes went on in the past. So if I know that running water is going to weather a rock, I have to make the jump in the assumption that a million years ago, running water is also weathering rock. That way, when we see things, we can then say, oh, yeah, that's caused by weathering rock from running water. And then we know what happened back then by applying what we know now. All right, principle of original horizontality, very simple. It just states that rock layers form, sedimentary rock layers form horizontally in water environments. That's all it means. That's our starting point, so that when we see anything other than horizontal layers, we know something happened. All right, principle of cross-cutting relationships. Faults are broken, plains, broken rock, and intrusions, magma that cut across other layers. They have to be younger events than the rocks they cut across. You can't break these rock layers down here like this if you don't already have the rock layers there to break. All right, so the rock layers were deposited, formed, and then they were faulted. Same thing over here. You can't, this magma that was a magma body, this can't cut across layers of rock unless the layers of rock were already there. Okay. All right, principle of included fragments. This entire conglomerate is younger than the particles that make it up. Right? In order to make this rock, you had to have all these different pieces and you had to squish them together. So these pieces are all older, and when you squished them together and made the new rock, the rock itself is younger than the particles in it. A lot of these things are pretty common sense. Okay? Principles of folding and tilting. Remember we said layers form horizontally. So if you have twisted, folded, bent layers or tilted layers, that event that caused those layers to do that must have happened after the layers were already there. So we can get an order of operations. All right. All right, an unconformity. It's an area underground where we're missing some history. There was some erosion going on and we lost some layers of rock, so we don't know how much history we're missing, but we know there's a gap there somewhere. All right? It just means that we're missing part of the history. We'll never get it back. We just don't know how much. All right, how do we form an unconformity? First part, okay, so we've got an ocean, we've got a body of water, and sediments get deposited horizontally beneath the ocean, beneath the sea. They form layers at the bottom. They get compacted. They turn into rock, sedimentary rock at the bottom of the sea. Sometime later, you're going to get you might get some tectonic forces that cause uplift. Some mountains form, some continents collide, whatever. But those layers get pushed up and they emerge out of the water. There's a lot of folding that goes on. The layers get deformed and twisted. And since they're now out of the water exposed to the air, they start to weather and erode away. Right? Eventually, you see that they eventually, if they're exposed long enough, they'll weather down fairly flat. Right? Those layers of rock will weather down. It'll disappear, the material will get carried away, and the area will get more flat. It'll get flatter as you go through time. And then, if at some point the layers, there's some tectonic activity again, and the layers end up sinking back down under the water, more sediments will get deposited back on top of this layer. And so we end up with this layer right here, which is an unconformity. It's a buried erosional. Here's the erosional surface right here. This was exposed to the air and was eroded. Then it sunk back down into the water and got more sediments on top. And now we have a buried erosional surface. We don't know how long this was eroding before it went back down and got covered again. So we're missing history in there, right? We just know that we know what happened. We just don't know how long it happened. Right? All right. The geologic column. Geologic column is a term we refer to as the ideal sequence of rock layers in an area. Right? For example, I'll give you an example. Let's say I sent 3 people to 3 corners of New York. I sent one of you to Buffalo, one to Plattsburgh, and one to New York City. Different parts of the state, widely spaced. And I gave you a little hollow drills, little hand drill bits. And I said, when you go there, find an open field somewhere, drill down into the ground several hundred feet, and bring me up a core sample of the rock layers that are in that area. So let's say over here in Buffalo, we have a shale layer, a limestone layer, a conglomerate layer, and a siltstone layer, whatever. Right? And then up in Plattsburgh, the person brought me back a sandstone. This column has a sandstone, a shale, and a dolostone layer. And then down in New York City, they came back with this: limestone, conglomerate, siltstone, sandstone, and shale. What I can do is I can take a look at the order that these layers are in, and the mineral content and all that kind of good stuff, and I can maneuver and manipulate this around so that I can kind of sort of line up the layers that I think are probably the same age. All right, so it looks like I've got some yellow, quote unquote yellow. There's no yellow limestone, but in this particular color coded diagram, I've got some yellow limestone in both of those, so they probably are the same age. And right above them is this green, mint green conglomerate. So that's probably, if you look, it's right on top of it. So that's probably a younger layer than the limestone, and it's probably the same layer. Then we got this gray siltstone, which is younger than that because it's on top. But now look, now I can bring in that green sandstone. There is no green sandstone. Remember, it's just fake colors, okay? So we got some green sandstone, then we got some little blue-gray shale, and then finally we got some dolostone on top. And what we can do is we can kind of merge those together into one ideal column that we should be able to find. Now, we don't find it realistically in real life because of weathering and all that kind of stuff. But if we put them together, we really should see that. That's the ideal column that we should find no matter where we go in that location, in those locations. But because of weathering and how deep we dig and all that kind of stuff, we're not going to get this actual ideal column. It's just what we should get. You notice how we merged this layer, this shale layer is the oldest. Then we have a younger layer here, and a younger layer here, and a younger layer, younger layer, younger layer, younger layer. All right? All right, so now let's correlate these rock layers. Okay? Here's how we kind of do this. All right? Again, we got some false colors here. All right? I like to use a line to connect the layers that I think are the same. And you can do it however you want, but I like to be methodical about it. So I'm going to start at the lower left. You always start at the bottom anyway, because the bottom is always going to be your oldest layer. So I'm going to start with this gray limestone right here. All right, that's where my starting point is. All right, so now I look in the other two outcrops. Do I see any gray limestone anywhere? I don't see any in the second outcrop, middle outcrop, and I don't see any there, so I ignore that one. And now I move up to my black shale here. Keep looking over here. I don't see any black shale. Okay, well, now I got to keep going. I'm not doing so well right now. So now I've got a tan sandstone. But look, I've got a sandstone right there. So those are probably the same layer. Especially since now as I keep going, look what happens. I've got my gray siltstone is probably the same layer as that. Still nothing with the third outcrop. I've got a red sandstone right there. That's probably the same layer as that. Still nothing on the third outcrop here. I've got a brown limestone, but now look. Ooh, brown limestone right there. So guess what? I finally just pulled that third outcrop in. Those are probably the same layers, the same age layer. I've got a green shale and a green shale here. Oops, hold on. I've got this layer right here in between the limestone and the shale that's not accounted for in the other two columns. That means that in the other two columns, it was eroded away. It was weathered away. So we have to account for that. So we come back and we put the line where it's supposed to be. And then we draw in a little squiggly line. That squiggly line is representing an unconformity. That tells me that that black sandstone should be in there, but it's not. So I'm going to come up here again, and it should be in there, but it's not. I've got to account for that layer. Okay, now guess what? My first outcrop is all accounted for. So now I come over here and I get this yellow conglomerate, which also matches up there. I've got my brown siltstone there, and then my glacial till in the third column is on the top. So starting at the bottom, here's my first layer. In fact, I'm going to do this in a different color here. I'll change the color. Right? Here's my first layer, because that's the one at the bottom. That's the oldest. Now as I work my way up, here's my next layer. That's a little bit younger. And then that layer is a little bit younger, which, by the way, is the same as that layer. Now I keep going up. A little bit younger is going to be that layer, which is the same as that layer. That layer is the same as that layer. There's my next layer. That's a little bit younger. That's the same as those two right there. Now be careful. The layer that's just a little bit younger than the brown limestone is the sandstone over here in the third column, which means the 7 should be right in there. So we just kind of draw a little one to represent there should be a layer in there. All right. And then we have our green shale is a little bit younger. Our conglomerate a little bit younger. Our siltstone a little bit younger. And then finally our youngest layer is going to be our glacial till. So out of those 3 outcrops, we have an ideal column of 11 layers thick. So when we draw them, we would draw them like this. Okay? There's our 11 layers from oldest to youngest at the top. And that's how we correlate. We look for matching layers in different outcrops based on what's above what, what's below what, all that kind of stuff. Okay?